last 8 time slot. Okay, this one manage all the paths. So in terms of space, this is much less. Also faster than this because it used the instruction level operation. Problem?
We have an array for each page form.
It's the same problem, but it's less space. Okay, but still, this one managed last 8 times slot. Okay, so this is called the approximation. Okay, estimation, not the whole path. We are going to manage only the limited, the time period for the path, but reasonably work. Because we don't need something, the information 1 hour before, 2 hours before. Only the recently happened the operation. So this is the approximation algorithm for the LRU. So this is called the LRU approximation. Okay. Another approximation is the second chance. Means, so even as one of the students mentioned, each page frame manage how many bits? 8 bits. 1 byte. It will be still if you consider the 6 longer time slot you manage, it will be increased. So still the overhead in terms of space. So why don't we manage 1 bit per the page frame? 1 bit for the page frame. If this one is accessed recently, 1. Otherwise 0. And so on. Then, which means 1 bit for the page frame. 1 bit for the page frame. So when you search the victim page, what will be the victim page?
0.
The first 0. Okay? So first 0. In this case, this one will be the victim page. So starting from here, and then next. But worst case, if all of them are referenced sequentially, all of them are set as 1, then first round you cannot find the victim page. Then second round, the first one will be victim anyway. So we don't know which one is the oldest one, but after the round, all of them are used. So we will select the first. So that means a second chance. Okay, 1 round and second round, at most the second round you will pick the victim page. It's not the accurate than this one or the traditional, conventional, the LRU algorithm, but huge reduce the space. Okay, huge, and also this one, is very fast, the algorithm. So this is another the page replacement algorithm for the LRU. So LRU algorithm is there are a lot of various versions of the LRU algorithm, not only page replacement, the algorithm that use the cache or the buffer, they use the LRU algorithm. Another example, I think that this is the second chance algorithm. So we are going to manage the 0 or 1. If not reference 0, if reference 1. Also, 1 more bit is used for the modified and non-modified. Modified means what? There might be higher chance. When do you modify the data in the memory? When update or is recently loaded into the memory. Okay? Which means there might be higher if both of them are 1, recently used and recently modified. There might be higher chance to be reused. So we will keep. But if 0 for is non-used and the 0 non-modified, which means there might be lower chance to be reused. So we will select the first 0,0, the page frame as a victim page because it may be higher chance lower chance to be reused. Okay. So this is the enhanced version of the second chance algorithm. Okay. Also, not always the least recently used algorithm makes sense, but if some of the page has not been used a lot, there might be higher chance in some case to be reused, right? If, for example, if you have the uniformly distributed access probability for the page frame, there might be higher chance. So at that time, in the rare case, we can consider frequency. Just the frequency, least frequency used the algorithm, which means smallest count will be the replaced. And the most frequently, because it has been used a lot, there might be lower chance to be reused. Okay? So it's the opposite, the most frequently used algorithm. It depends the specific case. Okay? In the specific case, you can consider this one. Okay, so there's other several issues in the page management. Okay, one of them is when we allocate the page frame. How to allocate? So one of them is we always when do you need to allocate the pages? First time when the process is created. Each process has the same size or different. It has the different size. So some of the program need more page frame, the others are not. So if you consider the characteristic of the process, that is the priority allocation. So you can provide a different size of a different number of page frame. Or so if you just give the fixed size, it's a fixed allocation. Global and the local allocation means the global means so it doesn't matter. So the row is used for group 1. So when there is new student for the group 1, we are going to allocate only this area. That is the local replacement, which means some of the page frame are dedicated to the specific process. If you do not consider such a thing, just whenever we find the free page frame or any victim, so we are going to find the victim page or the free the seed, that is a global replacement. So local replacement, you need to consider the characteristic of each processor. So you can allocate find only the victim the page or the available seed only from this area. So that is the local replacement. Better performance, but it's you cannot get the full utilization or the maximum utilization of the page or the frame. Okay. Dressing is always the problem of the page replacement, as I introduced the last class. Sometimes the number of page fault is drastically increased when, as we have seen the example of the Belady's anomaly, depending on the pattern of the reference string, it can be repeated, so keep happening. This is one of the very simple example of the thrashing. So let's say that we have the 4-page frame. So this is the current status. The A is for the variable. So this page frame is used for A. Main function is here, and X is here, and B is here. Then, when you have a routine of this for loop, how many times? 100,000 times. The next time probably we need a free frame for I, right? One of them will be victim page. So we will take out, for example, A. Then, next time, the next instruction, you need the A. So you need to find victim page, how many times? 4 times of the 100, 400,000 times page fault will be happening. Okay? So this is called the thrashing. Thrashing is drastically the increase. This is the CPU utilization, which means the performance will be downgraded suddenly. So this is called the thrashing problem. So how can we avoid such a thrashing? So which means these are working together. So we consider the number of the pages as a group. So this is called the working set model. So working set model is from here to here, they looks like a pattern. Okay, 3, 4 will be happen together. In this case, 1, 2, 5, 6, 7 pages happen together. So we consider such a set of the pages as a group, then allocate together. Problem? Yeah.
We have all of them in the page frame, right? All the variables in the page frame, right? We have 4 variables. Yeah.
For example, here?
Yeah.
But I is not here.
why would you call the main again and again? Like it won't call main, right? It will only work in the for loop, right?
Main should be here the test. It's just the illustration purpose. It's not the real case. Okay. So each definitely we don't need the entire page frame for the one variable. It's in case of integer, it's a 4 byte, right? So, but it's illustration purpose. Okay. So to address that problem, we can make the group of them. Problem: how can find such a group? It's not easy. Even though operating system, take a look at all the instruction code, they cannot decide. It's kind of semantic level, meaningful level of the group of the page. However, using data analysis also, one of them is kind of visualization. This is the time. So then, this is the address of the memory. Then for each address means it's a page number. Okay, whether they are being used or not. In case of being used, you can the dot or the highlight. Then you can see something group of along the time, group of them working together. Group, and these are the group, and these are the group. You can see the group of them. So we can consider such a group of pages as the working set model. They will be allocated together and freed together. So this is called the working set model. The problem is how to find such a working set model. But nowadays it's better and better. Okay, so data analytics, eventually the machine learning, such as the AI, will be used. It changed a lot. Think about the computer architecture. Nowadays, the GPU replaced sometimes the older CPU for the such a neural network-based training model. So it changed the computer architecture, eventually operating systems. So there are a lot of opportunity to use such the AI model for the operating system also. And memory can be used for the program process, but that's not the only purpose. Also, whenever we read the data from the file in the file system, where it goes should be loaded into memory. Then the CPU can read the data using the instruction like the move. Okay, which means that if what is the general process of the reading the data from the file by the CPU. CPU interrupt and request to the controller process and send the data to where? The memory, and finally CPU read the data from the memory. Which means anyway, CPU there are several instructions you need. Anyway, the CPU read the data from the memory. Why don't we map the file and the memory space? So a file is memory address page, the frame number 0 always. Then CPU can just read the data using address page frame number 0. Okay? Actually the page and page table, then read the data instead of a lot of the instruction. So that is called the memory map file. So memory map file, so reduce the number of instructions, then eventually we can have the better performance. So it's a page by page. Specific page will be allocated for the specific file. So it's a memory map. Nowadays, many of the systems, they implement the system library like the read and write only based on the memory map. Which means that from your instruction, you can just specify the memory address, page number, to read the file instead of invoking the interrupt and send the request to the disk controller and disk controller return, then the interrupt, then finally scheduler, and instead of such the complicated processing, the number of instructions, that we can use the memory map file. Okay, so even nowadays the standard I/O will be based on the MAP. So you can find the specific system library memory map the file. So it's named mostly MMAP. So this is the memory map file. So physical memory, you can see that they are mapped to the specific the pages. Okay. I want to skip the example of the Okay. There are several things we need to consider in the memory management. One thing is the pre-paging. Pre-paging means, as I introduced at the beginning of this class, it takes time at the beginning of the process and when you start. So why don't we preload before you just start the program or the process? We preload the number of pages. That is called the pre-paging. So anyway, even though you are using the pre-paging, that doesn't mean that we can increase the utilization of the memory, but we can get the reasonable the speed of performance. And also page size, the bigger is the better, so we are not sure. Okay, it depends. However, nowadays it's the kind of trend to be the bigger and bigger page size. So normally the page size nowadays is a 4K. It was the 512 byte or the 1K before, but nowadays it's up to the 4K byte. So also some of the operating system, like the Sun Microsystem operating Sun OS, use the multiple different size of the pages, like the 1K with the 4K and so on. TLB we have discussed before, and also not only the by the operating system level, the page, the memory management, the algorithm, but also user sometimes should be in charge of the page to avoid the page replacement, page fault. Page fault, the user should be careful. Like this is an example that I introduced before. Okay. Okay, so that's the end of chapter 9. A little bit speed up. So this is a last class, so I'd like to call your attendance. First, the undergraduate first. The Gugyong. Okay. And Nasim. Mary. And Armando. Okay. Arsh. Tatiana. Dewey. Brian and Julie. Any other undergraduate student? Okay. Then move to the graduate. Listen to this, very slow. The canvas is very slow. Jinan. Sribasan. Tari. Oops. Tali here. What is that? And Binay. Okay. Nishant. Ready? Suman. Kumar. Shravan. Ritesh. Yashabi. Sasanka. Uduluru. Manasi. Chen. Binoy. Vivek. Okay. Ganesh Kumar Chapa. Ganesh. Jit Kumar. Lee Thai. Desai. Amit. Abraham. Sarah. Pradip. Ravindra. Prudugi. Namlata. Srujan. Nikita, Debbie,
Yes.
네. Rohan, Debbie Priya,
Yes.
okay. Debbie Aleka Madhu, Nishi, Hashita, After,
Professor.
yes. Abdul Ahad, Sitinder, right? Mohammed, Santosh, Venkata Tarun,
Yes.
okay. Padala, Rajesh, Somaya, Papaganti, Nupur, Manish, Sashil Parik, Pa,
Yes.
Ashata Patel, Rashwan Kumar Patel, Babar Patel, and Pata Hendam, Vivek Handyala, okay. Polishadi, Anil, here. Sriram,
Yep.
Nagarjuna,
Professor.
yes. Ravi, Rachala, Ravi, Rachala, Laganathan, Rathod, Sam, Ida, Sai, Halvi, Tidivanam, Tiwari, Tumukuro,
Present.